Well, let's consider this example that is extracted from Carleton University. And as you can see, we want to go from the origin, that is on the left, to the target with the shortest path. What I mean when I say the shortest, I mean the following. As you can see here, all the edges between the nodes, these are the nodes, A, F, and so on. And you can see that on the edges we have the weight that belongs with the own edge. What's the meaning of this weight? This is the cost of going from one node to its neighbor. So for example, the cost of going from B to D is 4. And again, the cost of going from D to B is also 4, because we have not a directed graph. So we can go this way and backwards, okay? So let's go on with this, but pay attention, because every node has assigned a heuristics. What I mean with these heuristics? This heuristics is something about the straight measure of the cost of going directly from the node to the target. It's, for example, the Euclidean distance. As you can see here, we have A, and the Euclidean distance from A to the target is the measure, the length of this line. So this line is 6, as you can see here, 6. It's not properly a weight. It's not a cost of going from A to the target T. It's something about the rule of thumb. It's something that approximately, if we can fly over all the edges, if we can go by plane from A to T, that would be the cost. But it's not directly the cost, because there is no edge with a connection between A and T. So this is something about the rule of thumb. And pay attention, always the heuristics, in order to get an optimal solution, heuristics must be a lower bound of the real distance. And as you can see here, the distance of going, for example, from A to T is 7 and 5. So here we have 12 that is greater than 6, greater or equal than 6. For example, let's say F. As you can see, the cost of going from F to T is 3, that it's the same than the heuristics from F to T. So let's start with this, and we're gonna study 3 different methods. First of all, we're gonna use the greedy. This method is only using the heuristics. On the other hand, we have the Dijkstra method. This method will not use the heuristics, will use only the weights applied on every edge. And finally, we're gonna see the A-star algorithm, that it's some kind of a mixture of both methods. As you will see, the greedy will be so fast in computation. So a minimum load of computations will be needed in order to run this method, while the Dijkstra assesses more candidates, more nodes to be on the final list of waypoints, so it will be so long to apply. But if you do some kind of a mixture of both methods, you get the A-star, that it's some kind of part greedy and part Dijkstra. Let's kick off with the greedy algorithm. As you can see, we start here. We are here in O, and we want to find the minimum cost path of going from O to the target T. But because we are using the greedy algorithm, we're gonna use only this information, because the greedy algorithm is a method that uses some information on the graph. And this information will be only the heuristics. So first of all, we are in O, as you can see. So our neighbors, our candidates are A, B, C, because we can move this way, or this way, because we have edges that connect the O with A, B, and C. As you can see, these are the candidates, and the minimum value of heuristics is 5, because B is closest to the target than A or C. So the next node to be visited is B. So now we disappear from here, we are here. Afterwards, B has A as a neighbor, D as a neighbor, E, and C. So we're gonna check. A is 6, C is 6, while D and E, as you can see here, both have the same value for heuristics. So we have a tie. So we can decide to go through node E or node D, whatever. So I have decided to go through node D, but that's my own decision. You may decide, for example, go from B to E because we have a tie. So let's suppose we disappear from here. We are on D, and as you can see, for all the neighbors in D that are A, E, these are not not yet visited nodes. So, as you can see here, from all the neighbors, we have T, and T has a heuristics of 0. So I decide to go directly, obviously, to T, that is the target. So as you can see, the list of waypoints will be O, B, D, and T, with the total cost of this path of 14, as you can see, 5, 4, 9, plus 5, 14. This is not an optimal method, but it's so quick to apply. So as you can see, we have reached the solution in only 3 steps. You will see that the other methods will take some time. Dijkstra will take a lot of time. The A star will be in between. But you will see that the solutions that will be given by these next 2 methods are more optimal with a lower cost of 14. Let's have a look at the Dijkstra algorithm. We start here again and we check now not the heuristics but the weights of the edges that connect the actual node with all the candidates, all the neighbors to this actual node. So as you can see, we have as candidates A, B, and C, and the cost of going from O to C, for example, is 0 because the cost of getting to O is 0, obviously, and we add this cost that is 4. So that's why we have here a 4, here we have a 5 because here we have a 5, and we have a 2 in here. So we obviously decide the minimum cost, so it's 2 in front of 4 or 5. So we have this. Now let's check the neighbors of A. Which are the neighbors of A? B, D, and F. But the method, the Dijkstra method, implies not to forget about this previously considered candidate. As you can see here, you remember we have a 4 in here, we have a 5 in here, here we had a 2, and now we have a 4 in here. Why? Because we have 2, that is the cost of going from O to A, and then the cost of going from A to B, that is also 2, so the addition results in 4. Then we have F, that is 14, is a huge value, and then we have 9, because we have added 2 and 7. Obviously, the next step is to consider B or C. Again, we have a tie, so we can decide either. We decide B, but we could have decided C, so that's not, we are not forced to go through B, but we have decided this. So now the neighbors of B are D, E, as you can see here in the figure, and C. But you can reach C by 2 different paths. You remember the 4, because it's this path, and then this, that it's a 5. Why? Because here we have 2 going through A and B, and then going to C, we have a 1, so it's 5 in total. Then 8 comes from 4 plus 4, 9 comes from 2 plus 7, 14 comes from 12 and 2, and 7 comes from 3 and 4. So now we have a huge number of candidates, and finally we decide C, because it's the smallest value, it's 4, you remember? That one that was a tie with this other 4. So now we reassess all the neighbors, and now, as you can see, the method continues until we reach T. So as you can see now in this step, we have this 7, so we decide about this 7, this E will be in the list of waypoints, and then the neighbors of A, B, and E, and as you can see, we have a tie in here, 8 and 8, so we can decide to go directly from V to D, or to go from B to D by means of E. It depends, whatever you want. So then we have decided to go, for example, from E to D. So then, now, finally, we have 2 candidates that are F or T. And as you can see, the minimum value is 13 in front of 14. So then we decide about this. So the path, the final list of waypoints is O, A, B. We can go this, D and T, or we have an alternate possibility, that is this, from O to A, B, E, D, and T. Both are the same, because they both have a total cost of 13. So what's the best? I don't know. Maybe the best is to go from B to D directly. Why? Because you don't have a turn in here. As you can see, we have a turn. And maybe we want to minimize not only the total cost, but also the number of turns. And here we have a turn, while here we don't have a turn. Whatever you want. I only want to say to you that when you have a tie with the cost, you must add an additional criteria. The A-star algorithm can be considered as a mixture of the greedy algorithm and the Dijkstra algorithm. As you may remember, the greedy algorithm is so fast, but it's not optimal, while the Dijkstra algorithm is not fast, but it's optimal. So the A star will be like getting the best from both methods. As you can see here in the figure, I have considered the weights for all the edges in the graph and also the heuristics for every node in the diagram. In this case, the heuristics is given by this table, and these heuristics have been calculated by the Euclidean distance. So that means the straight line, if you could fly, the straight line from the actual node, from the node you are considering, to the target. In this shortest path problems, you can consider the heuristics in two ways, mainly. First of all, the Euclidean distances, like this in this problem, or on the other hand, the Manhattan distances. These Manhattan distances are considered in those problems where you have, for example, some kind of constraints in the movement, when you can only go up, down, left or right, but you cannot go in a diagonal form, then you must consider the heuristics as Manhattan distances, for example. You can use either, but depending on the problem, there will be considered the Euclidean distances or the Manhattan distances. In this case, we will use the Euclidean distance, that is the straight line, if you could fly. So let's start from the original node, that it's O, and as you can see here, it has a cost of 0, but it has a heuristics of 8, because the distance from O to T, this straight line, is 8. But have a look at the neighbors of O. As you can see, these neighbors are A, B, and C, with the heuristics of 6, 5, and 6 again. Now, the A star algorithm runs in a similar way than the Dijkstra algorithm, but you are not only considering the cost of going from one node to the neighbor, but also you add the heuristics from this destination node to the target. Let's have a look at A. As you can see, the cost of going from O to A is 2, but then you have added 6. This 6 is the straight line, is the length of this straight line from A to T, is the heuristics of A. This 6 is the heuristics. So at the end, the A star implies to use not only the cost, but also the heuristics, and you add these two numbers. Then the result is 8. Here, as you can see, it's 5, because the cost of going from O to B is 5. And then you have also a 5, because 5 is the straight line distance from B to T. So it's 10. Then again, here you have a 10, but thanks to another reason. Here we have a 4, the cost, and the heuristics is 6. So the minimum value, because you want the shortest path, the minimum cost path, is 8. So let's go now to consider the neighbors of A and again the neighbors of O, as you may remember from the Dijkstra procedure. Then, for example, let's have a look at the candidate B. B has an heuristics of 5, so that's the reason of this 5. And what's the reason for this 4? Because you have 2, that is 4, because it's the cost of going from O to B, but passing through A. As you can see, it's this route. So this route has a total cost of 4. You forget, as you can see in this case, the heuristics of A. You only consider the heuristics of the candidate. In this case, we have B as a candidate. So that's why it only appears this 5 in here. So the total cost is 9. Here we have again a 10, you remember, from the previous step. Then here we have a 12. Why this 12? Because you have a 2 plus 7 equals to 9. And as you can see, the heuristics of D is 3. So that's the reason for this 12. Here we have a 17. Why? Because we have 2 plus 12 is this 14 plus 3. That is the heuristics of F is 17. Then here we have a 10, as you can see here. So the next step will be to consider B because it has the minimum value. Then the neighbors of B, as you can see here, are D and E. And then the neighbor of O, as you may remember, is this C, that is this 10 in here. And then this F that has assigned a huge value, and it seems that it will not be part of the final list of waypoints. But we will see. Here we have a 12. This 12 in D is thanks to this. Here we have 2. Here we have a 7. So it's 9 plus 3. And as you can see here, we have another way to go to D, that is 2 plus 2 plus 4, so it's 8, plus its heuristics, that is 3, equals to 11. So now we have to decide between 12, 11, then we have here another 11, here we have a 10, and here we have a 10. So we have a tie, as you can see. Here we have a 10 and a 10 that both are the minimum value. Let's suppose we decide about E. Then we consider the neighbors again. As you can see here, F stays the same. And then from E, we have two neighbors. We have D. You remember here we had also 8 plus 3 equals to 11. Here we have again this. And then, as you can see, we have also another new neighbor that it's 14. Why this 14? This 14 comes from this 7 plus this 7. And in this case, 7 plus 1 leads us to this 8. And as you can see here, this 14 has an addition of 0 because the target has no heuristics value. So we decide about 11. And as you can see here, we have a tie. So we can decide by E or directly from B to D. Let's say that we decide to go this way, from O to A to B, B to E, and E to D. And as you can see, finally, for all the neighbors of D and the neighbors of the previously considered candidates like this and this, we have the minimum value that it's 13. And this 13 is because we have an 8. This is the total cost to get from the origin to D, is the minimum cost, and then we add this 5. So this is the 13 plus 0, 13. So our final list of waypoints is O, A, B, E, D, T, but the same way that happened with the Dijkstra, we can consider to forget about this turn and go directly from V 2D. So it's a synonymous solution. But we can decide for any of these two solutions. And can you see that the total cost is 13, that it's the same of the Dijkstra algorithm and it's smaller than the greedy algorithm, which is faster, but it's not optimal. And as you can see, the steps we had followed from the A-star algorithm are lower than the number of steps we have followed for the Dijkstra algorithm. You would have noticed this if we had a huge amount of nodes. When you have a huge amount of nodes, like GPS navigators or video games, the optimum algorithm is this A-star. Why? Because it uses not only the weights of going from one node to another node, but also it uses the heuristics of some node. These heuristics helps us to go in this direction, in the direction that is close to the solution, to the target. So that's the point. That's the crux of the problem. The A-star algorithm allows us to save some computing time because it uses the heuristics. Thanks to these heuristics, if you had a huge amount of nodes in here, a lot of candidates, A-star forgets about those candidates that are not on the direction of the target of the problem. And that's so interesting in order to save some time when we compute the solution.